Welcome to this explainer. Today, we're unpacking the architecture behind some of the absolute most powerful technology on the planet. We're talking about deploying and scaling high-performance AI computing infrastructure. So, if you've ever wondered how the massive physical data centers powering today's AI revolution are actually put together and, kept running, you are definitely in the right place. We're going to explore Supermicro's data center building block solutions.
But before we get into the real nuts and bolts of it all, let's start with a foundational question. How do you build a massive AI cluster without it melting down? And I mean that almost literally. Modern AI data centers face a huge existential threat from extreme heat, staggering power consumption, and just massive logistical nightmares. It's kind of like running 1,000 high-end gaming PCs in a sauna. When you pack that many advanced GPUs into one room, the physical laws of thermodynamics basically become your biggest bottleneck.
Well, the answer to that threat lies in this core concept right here: building block solutions. Think of this as a modular architecture that divides wildly complex, massive server clusters into smaller, interconnected, scalable units. It essentially takes a staggeringly difficult engineering problem and turns it into an intuitive, almost Lego-like concept. The idea is simple. If you can build one perfect, scalable block, you can multiply it to build an absolute empire.
Okay, let's dive right into our blueprint for this explainer. First, we'll look at core compute and storage. 2. Advanced liquid cooling technology. 3. Scaling to the rack. 4. Smart management and automation. And finally, 5. Global deployment and support.
Kicking things off with Section 1, Core Compute and Storage.
So this is the foundational element of the AI data center. It's the absolute micro level where the actual processing happens. We're looking at Supermicro's highly versatile AI and compute portfolio. And I want to point out, you aren't just looking at generic metal boxes here. You're looking at highly specialized engines. This incredible variety is exactly what allows the data center to be custom-tailored to specific, heavily demanding AI workloads rather than just settling for some one-size-fits-all approach.
To really understand the power of this brain of the operation, let's top specs. These systems support the absolute latest AI and compute tech from NVIDIA, AMD, and Intel. They range from compact 1U servers all the way up to massive 10U form factors. They also integrate petascale NVMe and SAS storage for those incredibly data-heavy AI workloads, maximizing throughput. And, crucially, these systems are designed from the ground up for either your traditional air cooling or advanced direct-to-chip liquid cooling.
Moving right along to Section 2, Advanced Liquid Cooling Technology. If those compute servers we just talked about are the brains, well, this is the bloodstream of the data center. And this brilliantly illustrates the direct-to-chip cold plates attaching directly to the CPUs, GPUs, and even the memory modules. They're capturing heat right at the source with incredibly low thermal resistance. From there, just follow that flow. That hot liquid is routed via optimized hose kits directly into the coolant distribution manifold, or CDM, which is mounted right in the rack. The CDM organizes this entire flow. It distributes cold coolant to the servers and returns the hot coolant, which saves a ton of crucial space while drastically increasing rack density.
All right, on to Section 3, Scaling to the Rack.
Now that we have our perfectly cooled compute node, we can zoom out and start snapping our building blocks together. The logic here is just beautiful in its simplicity. Step 1. You've got your single system node, that liquid-cooled brain we literally just discussed. Step 2. You take groups of those systems and network them with rail-optimized topology to form a scalable unit. And step 3, you just multiply. Because the networking, power, and cooling are all integrated at the unit level, achieving something as massive and complex as a 256-node cluster isn't some bespoke engineering nightmare anymore. It's simply a matter of multiplying your scalable units.
But of course, multiplying means a lot more heat. That's exactly where this essential piece of equipment comes in, the in-rack coolant distribution unit, or CDU. This unit integrates seamlessly into standard EIA or OCP rack architectures and handles a massive 250 kilowatts of cooling capacity per rack. What you really want to note here is the reliability. It features redundant pumps, so if one fails, the system stays online, securing your power and cooling continuity without skipping a single beat. But what happens when you need to scale beyond a single rack to an entire row of servers? Well, the building block methodology scales up the cooling right along with it. You have options like the liquid-to-air sidecar CDU, which gives you up to 200 kilowatts. But check out the in-row CDU option. That scales all the way up to an incredible 1.8 megawatts of cooling capacity for the row. To put that into perspective, that is exponential scaling.
It ensures that as you multiply your compute blocks, your cooling blocks grow right alongside them to handle that staggering thermal load.
Which brings us to Section 4, Smart Management and Automation.
Hardware is truly only half the battle here. You literally cannot manually manage tens of thousands of liquid-cooled GPUs. This is where the nervous system comes into play, an end-to-end software suite broken into 3 distinct arms. First, the SuperCloud Automation Center handles your enterprise-grade deployment, everything from firmware and OS provisioning to Kubernetes. Next, SuperCloud Composer provides unified rack scale and liquid cooling management. And finally, SuperCloud Director optimizes performance and developer agility by giving you multi-tenant AI cloud control, handling everything from bare metal all the way to Ethernet and InfiniBand networks.
Now, what's really interesting about this slide is the SuperCloud Composer interface. Operators aren't just looking at standard server loads here. They are actively monitoring the physical health of the entire data center. We're talking advanced power management, leak detection for the liquid cooling systems, and unified real-time alerts. It gives operators total 360-degree visibility and protection across servers, PDUs, CDUs, and yes, even third-party systems.
And finally, Section 5, Global Deployment and Support. So, you have the blocks, but how do you actually build the physical facility? Well, the building block philosophy extends way beyond the server racks to the site infrastructure itself. We're talking about massive water cooling towers that can support capacities anywhere from 1 megawatt all the way up to 50 megawatts or more. It includes complete site-scale cabling design to significantly reduce your material costs and labor. And crucially, it includes white-glove on-site deployment and global support options with an incredible 4-hour response time. The entire goal here comes down to one essential business metric: accelerating time to online. It completely bypasses logistical bottlenecks, so your new AI cluster can start generating real value immediately.
Now, actually deploying this much hardware globally requires an immense backbone. And this kind of scale is driven by major manufacturing and R&D hubs like Supermicro's Green Computing Park in San Jose, California. This is a continually expanding facility that spans over 1.5 million square feet. It's this massive physical footprint and manufacturing capability that makes it possible for these complex liquid-cooled building blocks to be validated, shipped, and brought online worldwide. Let's move to and see how this all builds into our grand finale. Ultimately, this micro to macro journey builds into a fully realized, large-scale AI cluster spanning the entire data center floor. Just look at the flow here, from the massive cooling towers outside, pumping cold water through the red and blue distribution pipes, down into the in-row and in-rack cooling units, and finally directly to the chips inside those compute nodes. The micro seamlessly integrates with the macro. It's an incredible feat of engineering. So, the absolutely crucial takeaway here is this: the extreme complexities of heat, power, and networking in the AI era are no longer insurmountable barriers. By utilizing a modular, liquid-cooled architecture, deploying petascale computing becomes, well, systematic. Which leaves us with one final, pretty exciting thought. If scaling up is really just a matter of connecting the right building blocks, how massive will your next AI cluster be? Thank you so much for joining me for this explainer. Keep learning, and I'll see you next time.